Welcome back. Today we are actually starting a new chapter. The new chapter is called as wave optics. So you can see that we have moved from ray optics to what is known as wave optics. So what is this wave optics? Generally, till now we have considered light as a ray of light or a beam of light which travels in straight line and things like that. Now we are going to move on to basically consider light in a slightly different way. Okay, so this happened actually many times. Flip flop of what light is as theories happened in the history. You can see that even as old as Newton's days. Newton actually was the one who became very famous when he actually published this his treatise called as Optics. Okay, so he came with this, he wrote like this actually, optics. He came with optics as a treatise on light, how light behaves, and he came with what is known as a corpuscular theory. Corpuscular theory, which simply says that light is made up of small particles. What he called them as corpuscles. It's like the light when it travels in air, it is almost like from the source some bullets are getting fired, like particles coming towards you. So they go in straight line, and he was able to very nicely show reflection happens. And even if you take a ball and hit it, or a carom board, if you hit it, the reflection angle, law of incidence is equal to law of reflection will happen anyway. So similar to that, these small bullets called corpuscles also behave. In fact, even before actually Newton, in even as early as, let us say, 1637, Descartes came with this corpuscular theory. Okay, so very long back. And when he came with this corpuscular theory, he actually was the one who talked about how it travels like particles and all that. But it became really famous after Newton actually introduced it, because Newton was very popular and is very influential during those days. So after he put forward the case, it became very it became kind of known to everybody that this is what is the theory of light. It was accepted as the theory of light. However, you have to understand that there was actually there is one problem with this theory. Okay, the problem is, let's understand this problem. It's an interesting problem. You have a reflection you can easily explain. Okay, let's understand this refraction. What happens in a refraction? Refraction is, assume that you have this water. Okay, this is basically my surface of water. I keep some water here, and this is all water. Okay, now let's say I'm going to basically fire bullet through it, the water. Okay, so I'm just basically going to put one bullet like this into the water. So can you tell me whether the bullet will go straight inside the water, straight like this, in this path, or will it go like this, or will it go like this? So this is a very easily doable experiment. You don't have to use a bullet. You can use a stone and throw the stone inside the water when you are standing with a certain angle. Okay, and see when it is dropped from straight, it might go straight. There is no doubt about that. When there is a certain angle of incidence, okay, how does the bullet go? So this question people have asked and figured out that actually the bullet takes this path, the path A, okay, and not path B. Everybody knew it doesn't go straight. Okay, why doesn't it go straight? Because the velocity or the speed of the bullet in air and water, if you see, okay, speed of the bullet in water I will call as basically VW, and this is V air. VW is smaller than VA. That means if the bullet goes slowly in, say water friction is higher, it goes slowly in water, and hence the it actually takes this path. It bends away from the normal, bends away from the normal. Now, this is how particles behave. Okay, any particle you take, it behaves like this. So, however, what they have seen is the light actually, okay, light does not behave that way. Light behave differently. This A is bullet, whereas the light is like B. This is the light. Light bends towards the normal. Your I and R, if you measure, R is smaller than I in the case of light. So, what does that signify? That signifies actually, if you suppose do the experiment the other way around, if you actually take a bullet and fire it like this, instead of going like this, the bullet will go like this. Okay, whenever there is, so sorry, bullet will basically go like, I'll put it like, bullet will go like this. Which means whenever a particle goes from, okay, a medium where the light, medium where the velocity increases as it passes through, okay, velocity when it increases, then it bends towards the normal. So, if velocity of light in water is greater than velocity of light in air, okay, then bends towards the normal, light bends towards the normal. So, go through this logic mentally, okay. We see that it bends towards the normal. From that we conclude that velocity of light is more in water than in air. But this was something, okay, which they did not know then. What is the velocity of light in air and what is the velocity of light in water was not known. In a denser medium, whether the velocity will increase or decrease, that was not known. Okay. So, they realized, and the people kept doing experiments all over the century, okay, and they realized that actually the velocity of light really is smaller in water than air. So, that is something that they kept on realizing with many various experiments, but they still could not discard this theory. Okay, this theory says that it has to be, velocity of light has to be bigger in water, but our lots of experiments are suggesting that though they couldn't really measure it properly, they were finding experiments which will kind of show you that in water it goes slower than in air light. Okay. But people were not convinced because the Newton has said that it has to be corpuscles. Okay. On the other hand, what happened was this guy called Christian Huygens. Okay, he came in the later years. Okay, this Christian Huygens came in 1678. He actually talked about. He's a Dutch physicist. Okay, his name is AAN actually, Christian Huygens, Huygens. So remember the spelling properly. Okay. Christian Huygens proposed this theory called light is actually a wave. Okay. So, because it is a wave, it is actually behaving the way it is behaving. He came with theories on showing if it is a wave, how you can show when the frequency, when the velocity decreases, it can bend towards the normal. He showed that. Okay, when he showed that, suddenly you realize that it is basically wave, but still people didn't believe. The people didn't believe it for a long time. They still kept on basically talking about that being a uh, particle, light being a particle. However, there was another guy called as Thomas Young. Okay, so in 1801, 1801, see this, the distance. Okay, 1801, you have uh, Thomas Young, who did what we call as interference measurements. He has a double slit experiment and single slit experiment and all. Interference. So he showed light interferes with itself and produces something called as interference fringes. Okay, like somewhere it adds up, somewhere it subtracts, like a wave. Okay. Wave does that. Wave sometimes adds up, some subtract depending on the phase of the wave. So same way light does. So this kind of clearly shows another way of looking at light, why light is actually a wave. Okay. So you see, the actually what happens is, if you take the light waves, then whenever whenever you see, but however, one another important problem that he faced also was that's the reflection. So reflection was something which was easily explainable using a particle theory. Okay. But Huygens is the one who actually showed both reflection and refraction. Both of them can be explained using wave theory also. Okay. He came up with his wave theory and explained to that. But serious problem that everybody faced, including Young and Huygens, was that the light, when it has to travel as a wave, okay, serious objection to that is that you need medium. Okay. Waves actually, what is a wave? Wave is nothing but the disturbance of the medium, okay, that travels. So whenever there is a especially sound, when I speak here, the vibration inside my throat here causes the air molecules to vibrate, and it causes the air molecules to vibrate. Like the medium has certain elasticity, so even when air molecules is pushed like this, it comes back. Okay, so even if you take a solid, or even on a solid, you can make sound travel. So there is an elasticity. That elasticity in the medium is responsible for wave to actually move in the medium. So if there is no medium, a wave cannot travel. Okay. Generally, that is our experience. So, but however, we know very well that from light from various stars and the sun and all the other planets actually is reaching us. We know very well that there is no medium in between. There is vacuum. So how is it possible that light is traveling? So that means it may not be a wave. So this problem went on for quite some time. Okay. And in 1850 or so, okay, in 1850, there was a guy called Foucault. He is very famous for Foucault pendulum. He did lots of theory and experiments, everything. So Foucault actually measured the light speed in denser mediums and other places, and showed very clearly that light is slower in water than in air. So by then actually after all these things of having Thomas Young showing the interference which happens only in waves, and Huygens showing how refraction works as a wave, and all these things basically made our Newton's theories a little go back, and ultimately what was established was the theory of light as a wave. However, there was still this problem. Okay, this problem of the light requiring a medium was not sorted out till a person called as James Maxwell. Okay, Maxwell. He was also Maxwell also was somewhere in. I think he was also in somewhere this time only. Okay, in 1850-60s time frame, 53 or 55, 1855 maybe. Okay, he actually proposed what is called as the electromagnetic wave theory. Means the light is not a wave like what you guys think about. It's not a mechanical wave which doesn't need to move the medium, the particles of the medium. It is actually an electromagnetic wave where you have electric fields and magnetic fields actually vibrate. Fields vibrate, not the particles. The fields vibrate, means fields value of how much electric field is there, how much magnetic field is there, will keep changing continuously over in the space, and it travels, the energy travels in as electromagnetic field. So that is basically, he said, light is that kind of a wave. He even calculated the velocity of this light using electricity and magnetism, okay, and proved very clearly. He gave a nice mathematical foundation to show that a light actually is an electromagnetic wave, and because of that, it doesn't require medium, and hence, most of the problems were sorted out. Okay, saying that it was conveniently proved that light was actually a special kind of wave called electromagnetic wave, and this was existent for quite some time till Einstein came. Okay, and he demolished some theories, and the people who showed actually how some of the other properties like photoelectric effect and all those things cannot be producing wave theory, all that. So we will not get there. We will get there after our exploration into the wave theory. Okay, so now we are into basically comfortably into the wave theory. So let's understand now what is this wave theory. How did Huygens actually prove that refraction can happen when it is a wave. Okay. So let's see those things, and let's understand Thomas Young's experiments on interference and diffraction and all that. Okay. So after that we will move on to more complications about light. Okay. So let's talk about now Huygens theory. Okay, we will now straight away get into Huygens principle. Huygens came with a very simple principle. What he said was, if you actually drop a small pebble in a water, that's a stagnant water, you just dropped a small pebble, you can see that water actually forms the circle, wave goes like a circle like this. So it is like, so you can see that many circles like this actually form. So these circles keep traveling like this. So whenever you drop a small pebble at the here, so one pebble, one circle. Keep putting more pebbles one after the one, more circles will be traveling one behind the other. Or small droplets, you are putting small drop of water. So there will be, you can see that there is so many different circles which travel. Okay. So they always travel in all directions. Okay. Now if you see here on the face of the on the surface of the water, you can see that these lines are nothing but, okay, if you take the surface of water, I am from the side, if you see, okay, you see that the surface of water actually becomes like this. These are, each one of them actually is a circle. So whatever you dropped, it has gone up. Okay, it's maybe like this, like this. So wave, that is the wave that is traveling. So wherever the phase of this moment, like what do I mean by phase of this? So look at this. At this point, it has gone down, the water level. At this point, water level has gone up. At this point, water level is somewhat in between. Okay. Now, wherever the water level has gone up, at the same pace, same level of water, wherever is there, if I join all the lines, all of those points, it will become a circle. So that is what we call a wave front. If we join all the points which are actually of the same phase. It's called a wave front. A wave front in this case, what we talk about in the water case, is a circle. So your wave front for water wave is a circle. Now let us look at basically any other wave. Okay, like for example, in his case he talked about light wave, or you can even talk about sound wave. Any wave you take, okay, and you produce that wave somewhere here. That means you put a source of light here, or you put a source of sound here. Okay. Then what happens is that now it spreads in all directions, not just in one surface. Okay, it spreads in all directions like a spear. Okay, so each one of them now becomes actually a spear. So it's not a circle. So that sphere, if you see, okay, so wherever there are points of equal phase, same phase points, if I join, okay, so I will get a surface, and that surface is a wave front. Okay, wave front is simply nothing but it is called a surface of constant phase. So wave front is a very important construct in the case of Huygens principle. He said that the front of the wave front, is nothing but surface of constant phase. That is a wave front, and the wave front advances. Okay, that is basically how wave propagates. Advancement of the wave front. Okay, that's the front of the wave. Now, what is important is that he actually talked about how the wave propagates in a very interesting way. Okay, he says that, so assume that there actually you have a source somewhere here, okay, and when the source is somewhere here, let's say this is my wave front, means that it has come like this, okay, wave front moved up. So that this is all having constant phase. Now he says actually if you want to find, given a wave front at certain point in time, how to find the wave front after some time. So that is how you define wave front. So this is the wave front at certain point in time. Okay, let us take some points there, point 1, 2, 3, like that, some points we will take. Okay, and those points we will take as secondary sources. Okay, we will call it, this is a primary source, primary source. So we will take this as secondary source. This is a secondary source, and from there we construct our wavefronts, construct a circle around that. Okay, after some time where do they travel? So this point, where does it travel after some delta t, some time tau? Okay, assume that it is going with a velocity v, then v tau. Okay, tau is the time after some time. Okay, or we can call delta t if you don't want to call it delta t. So delta t is the time. So v delta t time frame, it will travel a little bit. So where can it travel? If it was a source here, okay, he says that you draw a small circle around this. So it would have, if there was a source here, it would have traveled everywhere here, correct? And if you take here, again it will like this, like this, like this, correct? When they are traveling like that, now he says that you draw a common tangent to these circles, common tangent. So common tangent to these circles, basically as a curve you draw like this. And he said that that was basically the wavefront. After delta t time frame, wavefront is this. So initial wavefront is, let us say, AB. After delta t it will become CD, wavefront. This is how you can define the wavefront, where it is moving. Given at any point of time, if you see a wavefront, so how after some time where it will be, you can calculate using this idea of a secondary source. It is not, you are not saying that there is a source there. That is the way to calculate the wavefront. Okay. Now, however, people ask the question saying that constant, if you want to talk about constant phase, or if you want to talk about basically is common tangent, why can't we draw like this? We can draw like that too. This is also common tangent. Let's call it as EF. EF is a common tangent too. So is that the wavefront wave movement? So he says no, this is called as back wave. He called them as back wave, and he said the amplitude of the back wave is 0 and the front wave is maximum. So like that he gave an explanation. Okay, so he did not give any solution to that why it is so and all that. So he just he just escaped from that. Okay, saying that no, there is no back wave, it all goes front only. However, though this has these kind of problems in his explanation, they were very successful in explaining how actually wave fronts can be used very simply to show how refraction and reflection happen. So I will explain that to you. So before that, you can see that whenever a light is coming from very far distance, okay, wave fronts may actually be like plane. Wave may be going like. So these are basically how it is coming. So if it is a plane wave front, so the next after delta time t, it will also be plane. Okay. So plane wave fronts are possible. So it depends on the source. How does it look like? If let us say if the source is actually a cylinder like this, a tube light, then your wave front will be actually also is a cylinder like this around which it keeps moving. It's not a sphere. Okay. So wave fronts can have various shapes depending on how the source is put and how it is started. And then at any point in time, if you have a wave front, you can calculate the next wave front using this technique. So these are what Huygens talked about. So let us just look at now how Huygens talks about in terms of refraction. So let's see what is refraction. So that is a very interesting thing. So let's look at refraction. So for refraction, let us take a denser medium. This is our denser medium. Okay, this is a denser medium, and top is a rarer medium. So I'll call this is basically refractive index n2, n1, 2 and 1. Okay. If you want to consider a wave, how do we consider a wave? Let's look at that. Okay. So we no longer take a single line. Okay, what we do is actually take this whole thing as a wave. This whole thing as a wave. Okay, so this is a wave which is moving towards this, vibrating and not physical vibration but electromagnetically. But Huygens didn't know, he is some vibration. So it's a wave. Now this is how it is coming. Okay, this part of the wave, first part of the wave has reached the surface, and second part of the wave, this side of the wave, hasn't yet reached the surface. It is still traveling in air or in medium n1, and whereas this one has actually reached the surface. Okay, and we know that when it reaches the surface, it slows down. Okay, when it slows down, let us say it has actually turned in some way. Okay, I'm showing one way of turning. Okay. Now the same way, let us say this also has turned like this. So if I take, for example, the time that is travelled by this side of the wave, okay, the other side of the wave. Okay, let me actually give some names for this so that it is easy to actually remember. Okay, this is a wave front. I will call it as AB. Okay. So now it is moving in the direction, let us say A dash A, okay, and B dash B. Okay, so this is direction it's moving generally. Okay. This is, I will put arrow here. You can see those arrows. So in that, so this point I will call it as, let us say, C. Okay. By the time that B dash B, that part reaches C, okay, let us say it takes time tau, okay, for light to reach. So B dash B reaches C in time tau. Okay. So the length BC is then equal to, okay, and if V1 is the velocity of light here and V2 is the velocity of light here, so length BC is equal to V1 t, V1 tau. In the same tau t, tau, in same time tau, okay, where does A1 reach? A reach, okay. So let's say how A actually is lower. This side it is, see this, some part of the light which is this side, okay, which is basically AB side, is actually traveling in air, okay, or rarer medium. The other one is traveling in a denser medium, which is, let us say, is um, slower. The slower means it travels lesser distance, not just, it won't travel up to here, it will travel somewhere here. So we will call that point, let us say, as E. And if I join these two, EC will be the wave front after tau. Okay. In time tau, A dash A moves to E. So AE will be actually equal to, okay, V2 into tau, because in here velocity is V2, AE is V2 into tau. So these two things we have established. ABC is equal to V1 into tau and AE is equal to V2 into tau. This length, these two we established. EC is our new wave front. EC is wave front. You can see that wave front actually has kind of turned like this. EC is our wave front. Now let's look at the angles. Okay, this is, if you see angle I, this is angle I, means let us look at what are the other angles here. Okay, so I'm going to basically take this angle. What is that angle? If that angle is I, and this angle, what is this angle? Let us look at. So this is I. Let me just make this area neat cleaner. This angle is R. So if this angle is R, this is 90 minus R. Okay, so this is 90. This is 90 because I am drawing it like to get the wave front. So this is, both these are 90. Okay. These are also 90. These are 90. Okay. Now if this is R, then, okay, this being 90 actually, this is 90 minus R. So in a triangle, in the triangle AEC, this is 90 minus R, this is 90, that is, should be R. Similarly, in this triangle, let us say, okay, this is basically I. If this is I, this side, okay, is 90 minus I. This is 90 minus I, and hence this is I. So we got I here and R here. Okay, so now we will calculate sin I by sin R. What is sin I by sin R? So sin I by sin R is what we call, we know by Snell's law we call it as refractive index N2 with respect to 1. Okay. Anyway, so sin I by sin R is what will come here, we'll see. So sin I is in this triangle, if you say ABC, this triangle. This is BC by AC, BC by AC, and sin R AE by AC. Okay, this is AE by AC. Okay, so BC we have been told what it is, V1 tau. AC gets cancelled. V1 tau. This is AE is V2 tau. So tau also gets cancelled. This will be equal to V1 by V2. See, he was able to prove that sin I by sin R is actually equal to V1 by V2. So this angle, by this angle, is equal to V1 by V2. Now if you take V1 more and V2 less, okay, to get this work, I has to be more than R. So because it is V1 by V2. So if you take V1 more and V2 less, okay, that means it is traveling from a rarer medium to denser medium. Okay, in such scenario, okay, you know very well that the numerator is more and denominator is less. So that means sin I should be more and sin R should be less. That means I should be more than R. I should be more than R means bends towards the normal. So when the light travels, he proved that when light travels from a high speed medium to the low speed medium, it bends towards the normal. That is actually what was the troubling the particle theory, corpuscular theory. There they have seen that it is not the case. Theoretically and practically they showed that in particles don't work like that. Whereas wave he showed very clearly that it works like that. So whenever it is traveling from a rarer medium to denser medium, it bends towards the normal, and he proved exactly the same as this. This is our Snell's law. Okay, so this can be written as V1 N2 by N1. If you take N2 as with respect to vacuum, okay, if you are going from one medium to other medium, each medium N1 is simply saying that its refractive index with respect to vacuum. N2 is its refractive index with respect to vacuum. So if you take that, then it will become N2 by N1. Or you can also write this as 1 divided by N1 by N2, or 1 divided by N1 2. Something like that you can write. Okay, this is same as N2 1. So these are some of the different ways of writing it. However, this is our famous Snell's law, and he proved the Snell's law using Huygens simple wave principle. Okay, this is Huygens wave theory. So now you can actually say, why did I take it as already like this? Okay, why did I not take it like this? You can take it like this. Okay, and later prove that I is actually more than R if V1 has to be more than V2, and hence it will turn out to be the correct picture. Okay. However, when you go from denser to rarer medium, you try yourself. You draw a picture going from denser to rarer medium, and you can actually try the same kind of derivations even in that case. So this is a practice for you. Try it out. Okay, and there you can show very clearly why even whenever you have the critical angle coming up, so you can demonstrate that if it is more than critical angle, it will be total internal reflection. You can demonstrate that using that. So I will leave that for you to basically try it out. It's a very simple method to do it. Same method. So now I will actually move on to reflection. So reflection is even simpler. Okay, like reflection. In the case of reflection, okay, so you take a surface where backside it's rough, let's say, on the top it is smooth. I think my line is not sufficiently horizontal. Let me write properly. Okay, this is a good line, good enough line. Reflection. Now I will take um, a wave which is coming like this. Okay, and again this is my wave. So wave front is this. This is the wave front. This is 90 degrees. AB is my wave front. So let us see it reflects back. Okay, this is my normal at the point of intersection. Normal. And let's say it goes like this. The wave front is basically CE. So you see this is my wave front here. Okay, moving like this. This is the wave front here, moving like this. See these two lines come here and they go like this. It's a wave. Okay. So now let us look at incident ray and reflected rays. This is incident angle. Okay. So if this is I, then this, see, look at this, these two are 90 degrees each. Okay. So this angle is from here to here. Now that angle, if you see here, I will take the 90 degree from here, this one, and I will take the 90 degree from here, that is this one. Okay, two lines when they both of them move, rotate by 90 degrees, their angle preserves. So which is actually I. This is I. Similarly, okay, this is R. So this is R. So ECA is R and BAC is R. I. Okay. So triangle, consider triangles. Triangle ABC and triangle AEC. So those two triangle, if you consider, okay, angle AEC is equal to angle ABC. Write it like this if you want to. Is equal to actually right angle 90 degrees. And so side AC common to both. Okay. And let us look at this length AF, AE and AB. Okay. What is AE and AB? Okay. AE is equal to, so AE is equal to distance travelled by this one, distance travelled by the other side of the two of the, look at this. Okay, when for the side 1 goes here, side 2 goes here. Okay, so when side 1 hits here, it turns around here. Okay, by then when it is going here, this is actually going from here to here. Okay. When one is moving from A to E, 2 is moving from B to C. Both are in one medium, same medium, hence same velocity. So they have to be equal. Therefore, AE should be equal to BC. Okay, now you see here, AEC is the two sides are equal. Okay, two sides are equal and 190 degree RHS. Okay. Hypotenuse, this is the hypotenuse. By RHS, triangle ABC is congruent to triangle AEC. Once these two triangles are congruent, we can say corresponding angles and sides are equal. Hence, angle ACE, what is that angle? Okay, BAC, okay, BAC, angle BAC is equal to angle ECA, which is nothing but, which implies angle of incident I is equal to angle of reflection R. So, by taking wave theory, we were able to prove that angle of incidence is equal to angle of reflection. So, that is another success of Huygens. He showed it that by using wave theory you can do that. Okay. And what are other some of the other interesting things that he did was actually, okay, in his principle he talked about how to simply find out what happens when light goes through, okay, various things. Now you see how he is very intuitive his ideas are. Okay, let us say you are having a prism, okay, and light is coming like this, and its wave front is straight like this. So here is wave front. So constant phase is this. This is moving like this. This is your wave front is moving like this, and it hits here. Now the wavefront travels through this. When it travels through this, it's like it travels more space, more inside in the bottom of the wave. Okay, it travels for more distance in the bottom of the wave and travels very distance in the top of the wave. Okay, and we know that it is slow here. So for more distance, if you travel slowly, then you travel totally less distance you cover in a given time. Okay, so hence this part actually turns out, when it comes outside, if it is here, this part turns out to go a little further because it has only spent less time in this area. This has spent more time in the slow area. So the wavefront now looks like this, like this. So you can clearly see that this gives you an idea of how light actually bends like this. So very intuitively we can see why light bends there, okay, just by looking at Huygens theory. So powerful, very, very powerful theory that way. You take for example even a simple lens, and your wavefront is coming like this. Now when wavefront is coming like this, you see this side it travels less distance, in the middle it travels more distance, in the end it travels less distance. So wherever it travels more distance, it is somewhere here, next it travels somewhere here, this point is traveled somewhere here, this is like this. So after some time tau, you can say that this is how they have traveled various points, and if you join that, the wavefront will become like this. If wavefront will become like this, means it is moving like this, and hence it is focusing, you can say. Okay. You can take anything, including you take for example a concave mirror. If your wavefront hits it like this, and when it hits and comes back, you see it has traveled a longer distance, so it comes back only here, this comes back here, here, like this, it creates a circle, and hence it is focused. So he showed some intuitive ways of seeing why light behaves the way it behaves when you consider it as a wave, okay, using his understanding of movement of the wave front. So very interesting concept. Movement of the wave front can be used to show all these things. Okay, so that is how Huygens wave theory was very successful in showing a lot of these things. and even Doppler effect. Okay, so if you look at Doppler effect, he showed using Huygens wave theory. So we will discuss about the Doppler effect using Huygens theory in the next session. Okay, and we will also do some problem on the Doppler effect. Then we will get into addition and subtraction of waves, which is the foundation for understanding the interference of the waves, which leads us into the Young's slit experiments. We will spend some time on that. Thank you.